All right, next up is Kazutaka Matsuda on a language for partially invertible computations.
Hello, I'm Kazutaka Matsuda from Tohoku University. Today I'd like to introduce our new programming language, Sparkle, which is a language for partially invertible computation. Sparkle is named after a system for partially reversible computation with linear types. Let us start with the background, invertible programming. Invertibility is a common and important concept in software development. For example, we have compression and decompression, we have undoing and redoing, we have serialization and deserialization. Invertible programming is a way to provide correctness by construction. Then, natural question arises. For normal programming, the basic building blocks are functions. But for invertible programming, what should be the building blocks? An obvious approach is to use invertible function for invertible programming. However, this approach is restrictive because invertible functions have to be injective. But it is known that some functions become invertible after fixing some argument. These functions are called partially invertible functions. An example of a partially invertible function is an addition, which becomes invertible after fixing either of the arguments. A more practical example of a partially invertible function is Huffman encoding, which becomes invertible after fixing Huffman encoding table. Then, a question is it possible to do invertible programming through partially invertible programming? If so, what is a language for partially invertible programming? This paper answers to this question. We've designed a Sparkle, which is a programming language for writing invertible functions through composing partially invertible functions. This is because partially invertible functions are more natural and more expressive. Sparkle uses linear types, which is the key to correctness by construction. Let us start with an example to explain the problem and solution in more detail. Consider a function that computes difference of adjacent element in a list. Starting from 0, this function repeatedly computes the difference from a previous element. For example, the difference between 1 and 0 is 1, so it outputs 1, and the difference between 2 and 1 is 1, so it outputs 1. The difference between 5 and 2 is 3, so it outputs 3, and so on. This is a very simple function, but indeed useful. Actually, a variant of this function can be used as a preprocessing for image compression as found in Ping. The standard unidirectional implementation of this transformation looks like this. The subs take a list of int and returns a list of int. This function calls go with additional argument 0, which intuitively represents a previous element. Go takes int and a list of int and returns a list of int. If we apply goN to an empty list, it returns an empty list. If we apply goN to x const xs, it outputs x minus n and recurses over x and xs. Here we have some observation about invertibility of subs. First of all, subs itself is invertible. Actually, we can recover the original input from this result by using accumulative summation. For example, sum of this element is 1, and sum of these two elements is 2, sum of these three elements is 5, and so on. However, subs does not consist only of invertible functions. In fact, Go is not invertible but partially invertible. Specifically, Go(n) becomes invertible for any fixed or static n. This means that we need to care about partial invertibility in programming Go. This example also illustrates a challenge in partial invertible programming. that is, dynamic data flow into a static position. Here we highlight the dynamic part with blue. Here, x, which is dynamic, flows into the first argument go, which is static. Recall that go becomes invertible after fixing its first argument. To overcome the situation, we propose a Sparkle, a language for partially invertible computation. Sparkle comes with linear types and invertible types. Invertible types, denoted by A superscript R, intuitively means A typed values that has to be handled only in invertible ways. Thanks to invertible types, invertible functions are represented as ordinary linear functions between invertible types in Sparkle, like this. This representation provides a unified framework for describing invertible and partially invertible functions. For example, here we show the types of subs and go in Sparkle. Because that subs is an invertible function. In Sparkle, subs take invertible list of int and returns an invertible list of int. Because that go is a partially invertible function which becomes invertible after fixing its first argument. In Sparkle, go takes ordinary int and an invertible list of int and returns an invertible list of int. Sparkle also provides a pin operator to bridge invertible and ordinary bars. By using pin operator, we can convert invertible values into ordinary values locally in this continuation. Recall that it sometimes happens that dynamic data flow into static position, which is a challenge in partially invertible programming. This pin operator is a remedy for this situation. Let us start with a very simple example to explain programming basics in Sparkle. Sparkle is a linear typed higher order function programming language. Only the special thing is that it has invertible types. Here we explain how we handle values of invertible types. Here is a partially invertible addition written in Sparkle. This definition is very similar to the standard unidirectional version. But here, add function takes ordinary natural number and invertible natural number and returns an invertible natural number to highlight its partial invertibility. To construct invertible natural numbers, instead of using ordinary constructors, we use lifted constructors such as S superscript R. Here, we show the partially invertible multiplication defined in Sparkle. Multiplication, similarly to the sub-add function, takes natural numbers and invertible natural numbers and returns invertible natural numbers. Unlike the add function, the mul function uses case analysis on invertible natural numbers. To do so, it uses invertible branching indicated by invertible patterns like Z superscript R and SY superscript R. A special thing in invertible branching is a branch comes with condition. These with conditions are used in backward direction to determine branches, but we do not describe the details in this talk. Now we are ready to show how we program subs in Sparkle. Recall that subs is a function that computes differences of adjacent elements in a list. For comparison, we also show the standard unidirectional definition of subs in Haskell. The definition of the two programs look very similar, except the use of constructs that care about invertibility. Subs in Sparkle take an invertible list of int and returns invertible list of int. Surprisingly, the right-hand side of the SPARQL version of subs is identical to the unidirectional version. The goal in SPARQL takes ordinary int and invertible list of int and returns invertible list of int. To manipulate invertible list of int, the Go function uses lifted constructors and invertible branching. The most important part in the definition is that it uses the pin operator. By using the pin operator, we convert x of type invertible int into z of type ordinary int. Thanks to this conversion, we can call Go for z and xs. Recall that the first argument of Go expects int instead of invertible int. We say again that two programs look very similar. Indeed, they have the same recursion structure. This is a strength in SPARQL compared with existing reversible languages. Once we have defined invertible functions, we can use them by using the forward and backward functions. Here, forward is a function that runs our invertible function in the forward direction, and backward that the opposite. For example, if we apply forward subs to this list, we obtain this result. And if we apply backward subs to this list, we obtain the original list again. Indeed, a pair of forward subs and backward subs forms a bijection. This is what SPARQL guarantees. This is a brief introduction of SPARQL, but in our paper we discuss more things. For example, we define the core system lambda pi arrow of SPARQL. Lambda pi arrow is based on a linear calculus lambda q arrow, which is a core system of linear Haskell. The design of lambda pi arrow is also inspired by two-stage languages. We show some formal properties about lambda pi arrow, including type safety and bijectivity. We also discuss larger examples, including Huffman encoding and calculational development of tree rebuilding from in-order and pre-order traversals. Let us discuss some of related work. There are some existing results concerning partial invertibility. In program transformation, there is an inversion method called partial inversion and semi-inversion. Also, there are some reverse programming languages that support a limited form of partial invertibility. The design of SPARQL is inspired by our previous work, Hobbit. Hobbit is a higher-order bidirectional programming language in which lengths are represented as ordinary functions. More specifically, length between s and t is represented as an ordinary function between bs and bt. Here, bs and bt are very similar to invertible types in SPARQL. But Hobbit does not use linear types, and it does not provide the pin operator, which is very useful in partially invertible programming. Let us conclude our talk. We designed SPARQL, a programming language for writing invertible functions through composing partially invertible functions, because partially invertible functions are more natural and more expressive. SPARQL uses linear types, which is the key to correctness by construction. Thank you.
Thanks, Kazutaka. In either time band, you should see a Q&A link appear in Clowder that brings you to a video chat where you can ask Kazutaka your questions.